Thank you for this invitation. My name is Daniela. Now you know all about me. I would like to learn a little bit more about you. Who happens to be a beginner in C++ and wants to learn a lot? Please raise your hands. Cool. Who of you is a seasoned developer and knows how C++ works and is productive in it? Please raise your hand. Okay. Okay. And who of you knows way too much about C++, is totally disillusioned, and is a member of the C++ committee? Okay. I was expecting similar. So, who has an idea what this file name would be?
Is that CrowdStrike?
Exactly. This is from CrowdStrike. It's an update that CrowdStrike was delivering to about 8 million machines past year. And CrowdStrike, as you may have heard, is a cybersecurity defense system. And this update gifted these 8 million machines the ultimate protection against cybersecurity threats because they would not boot anymore. And this was covered by the news worldwide, and tens of millions of people were affected by that. And they became aware of the capabilities of CrowdStrike, I would say. So was this a marketing stunt that was a little bit too good? Or was it the result of a botched update that triggered the attacker that was already sitting in these machines? I mean, the cybersecurity defense system as well? Or was it just a bad engineering choice, selecting the wrong implementation language, as some Rustians would say? We don't know. But at least it made people aware about the thing that we call security vulnerabilities. And this is why I will be speaking in the next couple of minutes about security and safety, the safety in our code or the lack thereof, existing solutions that we already have but we can improve, and new features that will come up in C++ 26. And if we have the time, we can look into the options that we have for the future beyond C++ 26. A few words about me. I'm from Germany. I come from a very small company in the south of Germany, and we build machines like this one here. This is for passenger trains, the quality inspection machines that we use. That should be enough. 2 years ago, there was a particular document that multiple governmental organizations in the world gave out to speak about software vulnerabilities. And in there you find quotations from the major software development companies in the world, and pretty much all of them have observed that about 70% of the software vulnerabilities and the CVEs that they were experiencing are coming from memory unsafety. And if these companies come up with a viable solution to address these software vulnerabilities, they may no longer be eligible for governmental programs. So we need to find a way to deal with them. If we look on a different website, we find the so-called common weakness enumerations in there, or as I might call it, the list of shame, with the 25 most popular software failures that you can do in the engineering. And you find 6 particular topics in there that can be attributed to memory unsafety in C or C++. But what you also find, the rest of them are not related to memory safety problems. They're just other things that you might do wrong in software engineering. I have a question?
I would say the SQL injection is a text buffer overflow, so that's related, but not our problem.
Okay, thank you for the comment. This scares people, lists such as those. But on the other hand, other people have a different opinion on these software vulnerabilities. It depends on what you want to see from a particular system. Okay, so much for the boring part in the introduction. Let's go into what safety really means. You know, when people speak about safety, what is safety at all? And I've already heard memory safety, we have bound safety, probably. There are many different kinds of safeties that we can have, but we are not really interested in this kind of thing. What we want to see is, if I ask you what is your opinion about this particular picture here? What would you say?
Clean.
I see a flight of server machines in a data center. These server machines might hold valuable information that other people desperately want to see, like the latest cat videos on YouTube, or personal information or secrets. This is what this picture actually is telling us. And what we actually see here is security. This is the ultimate goal, the freedom of any software vulnerabilities that might be subject to exploitation and extracting information from these machines. And everything what you do in these particular environments, not only software questions, this must be a safeguard and a protection from known, unknown, and unexpected vulnerabilities. What do you see here? This is a picture that was taken about 10 years ago in our company when building a machine in a cage that is using a robotic arm, moving steel billets into an immersion tank and to transport trolleys. But you also see you have the emergency switches, you have the lights, you have the sensors in there. And what this picture essentially means, this is what we call functional safety. And functional safety is, simply put, protecting users from technology, and also vice versa, it protects technology from users. And both security and functional safety are system-level properties, not language-level properties. And in functional safety, we have multiple stakeholders. For example, users don't want to get harm from the physical side of things, but also from the mental side of things. And the owners want to make sure that these machines work exactly as expected and not facing too much wear and tear because of using these machines not in the intended way. And you have unions, you have insurers, all of them has a different opinion about these machines and what a vulnerability might actually be, and then affect the functional safety of these kind of problem. So this is the end of the theoretical part. Let's move on to the stuff that you hopefully are really interested in. Let's look at some code. I have a piece of code here, not too difficult. And I have two variables here, s and u. and you see the definitions of the types I'm using here. The first question is, how many objects do you see in these highlighted lines? Who thinks it's 2? Okay? It's a nice round number. 10 or less. Okay. A few more hands. More than 10. Nobody? Oh, one.
Oh, it's actually
Pretty reluctant. In fact, it's 16. It's not just the complete objects that count. We also have sub-objects and sub-objects of sub-objects. And if you count them, it's 16. Even more important, we have a couple of pointers that we form to refer to these particular sub-objects here. We have a couple of assertions to test for certain properties in there. We have a return value that it's passed out, and this is what this entire program does. I think we all can agree this compiles, and when it runs, it will return a 0 and say this is so fine. Okay, all sleeping, good. Yeah, this is no question, this works. Now, let me make a slight change. Now the 2 objects are no longer at namespace scope, but go into the body of the function. Does this change behavior?
maybe.
Maybe, yes? Let's see, let's compile it. And the first thing that, at least at a certain point in time, GCC was claiming about undefined behavior happening here. Because these 2 objects, they live no longer at namespace scope, where they get the 0 initialization. Now if they live in a different space, they don't get this treatment anymore. And as you know, reading uninitialized values and using the values that they get from, like here in this Boolean expression, is undefined behavior. And one of the first things that we did 3 years ago at the beginning of the C++26 cycle was giving this a new name. It's no longer undefined behavior in C++26, so it's erroneous behavior. Some people may say, okay, it's just a name change. What does it mean? It actually changes the world. Undefined behavior means the compiler sees this is something that is not according to the rules of the language. I'm no longer bound to producing a meaningful program. I can do whatever I want to do to improve the performance of a particular piece of code and call it a day. With erroneous behavior, this is no longer undefined. It's totally defined behavior, but it means it's an error. And compilers are no longer entitled to take advantage of that. In fact, the compilers are encouraged to diagnose this particular problem, hopefully at compile time, but maybe also if they can do it at compile time at runtime. Either way, this program would not work. Okay, so.
What do you mean would not work if it's at runtime? It would throw, it would crash?
It depends on what your compiler does in this particular case. You have to look up what the compiler says it would do in this particular situation. I didn't want to go into the details, but the question is totally right. What does the compiler do? I have not seen this feature implemented in any compiler, so I cannot answer what the actual behavior would be in this case. In this particular case, I would expect it to be diagnosed at compile time. Okay, So what we should do is just initialize these two variables. We have value initialization in C++ since a very long time. Just do it. This is the best recommended practice that I can give you. Let me make a slight change here at the end of the program. Does it change behavior? This is no longer a mutable value, it's a const expr value, a variable that I'm using here. Does it change behavior?
No.
You don't count, you know. Yes, no?
It doesn't have to be evaluated at compile time, right? If it would be const evaluated, right?
Const eval and const expr at variables make no difference. The value that the variable is initialized with needs to be known at compile time. So it will be evaluated at compile time. Does it change behavior?
It's not allowed with UB now when it's constant.
Exactly. So let us compile. And the first error that compilers would point out is not just because of the previously non-initialized variable. Now we have an out-of-bounds read that is diagnosed by the compiler. And it, for the most part, it will just be diagnosed at compile time. You know, this array is used one past the element. More problems? Okay. Here we have undefined behavior just as well. I'm trying to read from members of the union that are not active. These sub-objects in the union are not within the lifetime, so I can't access them in any way. Or better, should not. It's just undefined behavior. Yeah, and this is what undefined behavior actually means. We have seen no problem at runtime, but at compile time it has been diagnosed. In fact, at the current version of the standard, that is, as Harald mentioned it, in discussion in the national bodies, we have about 90 places in the core language where undefined behavior is mentioned. Does anybody know where undefined behavior is actually coming from? Why do we have undefined behavior? Are we, as committee, so clueless that we know what to do better?
From C?
It comes technically from C, then the question is, why does C have undefined behavior? It helps in optimization, sure, but it's not a reason.
Oh, standardization.
Excuse me?
Standardization after usage.
The point is, if you want to have a portable language that can be used in multiple architectures, and you make so many rules in your language that this particular behavior should be done in a particular situation, then this is easy for some of the implementations and pretty hard for other implementations. And what C and C++ are about is get the best performance out of your machine. And if you want to deal with any corner case that might come up, even if you would never use it in your code, you have to generate code for that. And this is why it's left out as undefined behavior. And ask us developers to not run into undefined behavior, because we are all perfect and we make no errors. The compiler can assume that the code that we write doesn't exhibit undefined behavior. But in fact, we have it 90 times in the language. So the best thing Yeah, this is fine. And as mentioned, this is why compilers can extract the most performance out of the... You have a question?
Yeah, so does it mean that, very concrete question, that you can no longer get the address beyond the end of an array?
You can.
Because I've seen there was an address.
You must not
before
evaluate what what's pointed to at
So
this
must not
particular
assume
address.
what is there after the end of an array. I should not assume the memory layout of what is.
Exactly, because in the real machine you don't know in advance
I
how
don't
the
know the
layout
packing.
of your
I
variables
don't know
might
the
be.
packing.
Excuse-
The packing, I don't know the packing factor.
You pretty much know nothing about the particular order in.
But I can still get the address at the end of the array.
You can still get the address.
Thank you.
I was using it in the program. I can form the pointers to them,
Yeah.
but I must not evaluate. This is where the undefined behavior actually lies. So we want this undefined behavior at runtime, just to make sure that we can use all these languages in pretty much all of the current implementations. So what do we do? How can we get rid of all the undefined behavior in our programs, or at least diagnose it and then hopefully handle it? You've already seen it. This is constant evaluation or compile time evaluation. This is by far the best tool that we already have. You see, the compilers are forced to detect all violations in our language rules. At runtime, we have undefined behavior. At compile time, we need to adhere to all of the language rules that we have. But we can diagnose them only if we actually run into undefined behavior. So we need to perform the execution of a program at runtime. And how is it done? Do you know that you have not only a C++ compiler, but also a C++ interpreter? It's built into our compilers. And this is what is actually used to evaluate for example, the initializer of the const expr variable that we've seen before. So we need to use points in or constructs in the language that force the compiler to actually evaluate parts of our code, like for example, an static assert or const expr or const init initialization of variables. There are more that we can technically use.
Is there undefined behavior which is not diagnosed in constant evaluation?
No, all of them are. So in fact, this evaluation at compile time is something that you would see, for example, in your tests if you have an address sanitizer and a better version of it. If you have an undefined behavior, a better version of it. If you have all the sanitizers that you can imagine, all the static analyzers, and perfect versions of them all run together. This is the kind of detection that you get from constant evaluation. All of the language rules are written down and need to be followed. There is no gap in there. Everything is detected. Have a question?
Yeah, so the difference between undefined behavior and implementation defined behavior. So in the case, for example, of converting a float to an integer that is overflowing the range of the integer, which depending on the architecture can either round it or can saturate. For example, compare the x86 to ARM. That's not undefined behavior, right?
If it's not undefined behavior, it will not be detected as such.
But if it is implementation defined behavior, or if it is architecture dependent,
then it's something
I mean,
different.
converting a float to an integer is what?
you know how to deal with that. If you use the angle brackets, then it's a narrowing, and narrowing is undefined behavior and forbidden at compile time. This is the way how to deal with such kind of situations. In many cases, people use just the assignment operator, and the assignment operator allows us to change the value ranges, but if you use the brackets, then you're fine. So C++, const expert is a thing that is known for a very long time. It started in C++ 11, or constant folding is even older than that. It started in Lisp. But in C++ 26, we have a lot of more. In fact, we have so much constant evaluation compatible stuff in there. It's much easier to enumerate the missing pieces that are not yet available at compile time evaluation. We are even thinking about coroutines at compile time, but there's a kind of implementation pushback. I really want to have a compile time fuzzing, but this would be a challenge. Okay, let's switch gears a little bit. Let's look at this particular piece of code. I know it's a code that should never pass any code review, but imagine this is from a large program where things are not as obvious. So we have an implicit contract here. We named the variable, the function parameter array, but who knows if it's actually an array? And how big is the array if it happens to be one? We cannot infer it from the function itself. There is no clue about it. But we still need to meet the implicit contracts that the index has to lie within the bounds of the array. This is what bound safety is. Yeah. Here's the problem. Even though if we say, oh, this is array and compiler, this is known at compile time, yeah, at a later point. We could use, for example, this particular construct, but who wants to hardcode the sizes of the arrays that do you want to use in a function? Okay, you try, for example, in a template, and imagine to deduce the size of the array. Unfortunately, this doesn't compile. Okay, let's make it an additional function parameter that then you have just shifted the problem from the function itself to the invocation of the function. Now you have to make sure that your arguments are actually matching. What you really should do, really should do, is use what I called contemporary C++, or easier, use strong types wherever you can. Follow the suit of Björn. He's teaching this to you probably for past 10 years or so, I would imagine, or even longer. Yeah, because we are still having a problem of not checking the index. But with C++ 26, even if we don't check the indices anymore, we now have the option to use the hardened standard library that does it for us. This is the proposal. And as far as I know, all major compilers have an implementation of the standard library that already implements this. So you can use it if you are not too far in the past. In fact, if you're interested in hardening the standard library, I would highly recommend to watch this particular video from past year. Louis Dion is a member of the libc++ team at Apple, and he knows a lot about the reasons and the techniques that have been used there. Just watch it. From the measurements that were taken by the major companies using a hardened standard library, they reported back, if you switch on the compiler optimizations, the amount of the performance impact that you might see from switching it on is in the low tenths of a percent. So this is totally affordable. And the latest report I got from Apple, in the WebKit team, they said, whatever you do, you must not have any performance regressions, and they can report they don't see any performance regressions. Whatever it means to your code, I can't imagine. The point is, whenever these library contracts that we already have in the specification of the language, they can be or should and must be checked at runtime if you happen to switch on the hardening. And what it does with the current implementations is immediately stop further user code in your process. And this is the thing that you would get from immediately stopping. You don't get any security problems anymore. And with another proposal that is coming in with C++26, at least, I hope so, we actually get a detour in a contract violation handler, that we can use it to actually improve the functional safety in our programs to handle such situations. And as I mentioned, it's already implemented in the major compilers. As far as I know, some of them even go beyond the proposal that you have seen before. They have more containers, more classes, more functions that are hardened according to the spirit of a hardened standard library. And I know it from the Microsoft standard library. They even had additionally what's called destructor pointer tombstones. So in the destructors of, for example, containers or unique pointers, you would see that you get a trap if you try to use the memory in a, for example, a vector after it's freed. So you even get hardening for this kind of stuff. I made a small test here. Without hardening, you get just a few random numbers. This is what undefined behavior means. And the program would say everything is fine. But with hardening, the program would immediately stop as soon as undefined behavior is happening in here. And you get a nice status code as a result of the program execution. So this stuff is not fancying. This is just real behavior that you can get. Any questions about the hardened standard library? Okay, let's move on.
Is the cost small also for this use after free?
Yeah, but you need a little bit of compiler cooperation, because what it actually does is all the, for example, the pointers to the memory allocated in a vector will be given a poisoned value that would trap the compiler if you try to use the referenced sequence of values in a vector.
Yeah.
And technically, compilers are not required to actually generate code for the assignments of a that variable in an object that is bound to die in a destructor. And it depends on your compiler if such things are possible. This is why I mean you have to have a compiler cooperation to actually get this kind of protection in there. I know it only from the Microsoft compiler who does it. I'm not sure about the libc++ and libstudc++ and Clang and GCC. Have you seen something similar? No. I would assume this is a pretty compiler-specific thing. So, as already mentioned, if you have a hardened standard library,
Like the hardening, is that a opt-in flag for the compiler, or?
It's an opt-in. If you have the idea that paying the price for hardening is too high, it might be, it depends on your particular code, then you can opt out. But you lose the benefits of a hardened standard library. In fact, the entire committee said, we want this, we really want this. It was, as far as I know, the only proposal that ever got unanimous consent, which means not even a neutral vote. Okay, Dirk?
Yeah, I was wondering about talking about the very low percentage performance with range checking.
Yeah.
Do you think that's mostly because of modern branch predictors, or do you think there are reasons?
I don't know. They didn't tell me what the reasons were, but this is what their observations have been. And in particular, I found it so cool that the WebKit team, who must not have any regressions at all, could report they have 0% of performance to pay using the hardened standard library. Maybe they know more than I do. What I wanted to say, current implementations don't have this particular proposal. They implement this immediate stop, no longer execution of user code in the process. This is good for the security people, but it's a disaster for the functional safety people. If you have a machine that has a moving robotic arm, you must do something as soon, even when your program is behaving badly. You must bring this robotic arm to a stop, or whatever it might need to guarantee functional safety and not harm any people. And for these people, we have this proposal here, P2900. I heard a little bit about it before. This is the contracts thing. This is similar to what older languages already have, and you probably heard about contracts before. It's for us, the developers. It helps in what we call design by contract, and it's there to check correctness. And what we do today, if we have contracts in our programs, or better don't, the only option that we have is use, for example, comments to tell the users of our functions, please make sure that you use it correctly, and then I will give you this guarantee of an outcome of a function. And you also can use the assert macros from C if you want to make sure that a particular expectation holds. The problem is, if we execute this code out of contracts, not all of them would be caught by the assert. And if you compile it in release mode, none of these contracts would be caught at runtime. This is not what we want to have. So what you can do if we get this function, this proposal implemented in compilers in C++26 is we now can annotate our functions, the declarations, that we have a precondition here, This is a Boolean expression, just regular C++ code. And please, it's meant to be redundant. Don't do anything in your expressions that you put into, for example, a precondition statement here. You could do the same in the postcondition.
I was wondering, are the pre and post conditions part of the function signature, or?
They are part of the function signature. This is the major point here.
Excellent, thank you.
You don't have to know something about the body. And yeah, you can, there's another thing here I mentioned. It should be redundant code. Redundant code, it works without all the checks here to make sure that you don't do any meaningful stuff to the functions that are, to the arguments that have been given to the functions. They will be implicitly const when evaluating these Boolean expressions in the pre and post conditions. You cannot fix up bad function arguments here. This is why we have this constification here. You can also do it within the body. This is the contract assert, and this is where all the discussions are coming from. In all of these cases, it's in the preconditions, the postconditions, and in the contract assert. We also have this thing called splitting our code into what's called now epochs. An epoch is a particular section in the code where, let me put it this way, if you have any observable behavior in a particular piece of your code, and later on you might have undefined behavior that would do whatever it might do, it's guaranteed now that the observable behavior in a particular epoch will actually happen before entering the next epoch. This is also good for functional safety. If, for example, in a particular epoch, you instruct your machine to stop, and then later in the next epoch it would run into undefined behavior, you are guaranteed that this observable stuff in the previous epoch is actually carried out. Any questions?
Yeah, is this required to be across compilation units also? Noticing this in
This is just one function. This is in one function.
Yeah, when you have call function down there, it says function 3 violates the assertion there.
I'm not sure where you see.
Row 18.
Yeah, but here in this particular example, it would split the function body itself into 3 epochs.
When is it global? Is it
Um,
outside the assertion?
Yeah, the pre and post condition would split.
Okay, I was looking at 18. How does 18 know that? Yeah, the
It doesn't
violates
have to. It doesn't have to, because if you, you're pretty a little bit ahead of time, but anyways, let's go here. If you, for example, go into line 18 and you call it, you would execute the precondition, and the precondition would split your code evaluation.
Does it mean you disable the preemptive execution that all the processors have, so that basically the kind of bugs Spectre was exploiting? So does it mean you disable that? Because no way is it observable, because that's the thing that you have to work with the processor cache and so on and so forth. It's like I forgot exactly the term what it means. It's the bugs that Spectre was exploiting. The execution that goes forward and then it has to be rolled back and then
The shadow execution?
yeah. That's
Or
the thing
or
for
brands?
the
Branch prediction.
branch
Yeah.
prediction.
Yeah.
This wouldn't help you here. The
When
compiler
say
implementer has to make sure that it
compiler
happens.
does disable that or in which way?
Not at all.
What does observable mean?
What observable behavior means, we speak about language.
Yeah,
The language, if you look at the C++ language, you have the abstract machine. The abstract machine is performing stuff. And some of the code in the abstract machine is visible to the outside world. For example, output functions or writes to registers in your machine that are marked as volatile. This is what is meant with observable behavior. We are not talking about what's going on in your particular CPU. If you, for example, you have been mentioning the Spectre kind of thing, this has nothing to do with that kind of thing. Any more questions related to this? Okay.
You mentioned that the pre and post conditions are part of the signature. Does it mean that they are evaluated by the caller also?
Yeah, good question. In fact, we cannot and will not guarantee how many times any of the pre and post conditions are evaluated. For example, if you put the lines 3 to 5 into a header, then you have one particular translation unit who would be using this function and see these pre and post conditions and might evaluate them on the caller side and put the implementation of the function in a different translation unit and sees the pre and post conditions and evaluates them again. This is why this is necessary, in fact, if we have the split between different translation units. The compiler cannot see across translation units. So, depending on contract evaluation modes.
But you can't omit it from the header file, but then have it in the translation unit.
You technically, the pre and post conditions can be seen. Now we go pretty deep into details. It can be seen as being part of the function itself, the function body, and they can also be seen as part of the caller side and what's going on there. So, depending on other things, the Boolean expressions here in the pre and post conditions can be evaluated 0 times, 1 time, 2 times, or possibly even more. So don't do complicated stuff in your contract evaluations. As mentioned before, it should be redundant code that doesn't do any meaningful stuff.
Does this restrict function pointers?
Let's put it this way. This proposal is the minimum viable construct. And minimum means some people think function pointers are not considered to be beyond minimum. So no, the current proposal doesn't include function pointers. There are proposals that address this. This is how it is. It's just the beginning of the full entire thing. But still, it's pretty useful, I would say. Yeah? Excuse me?
Virtual functions are also.
Exactly.
I'm gonna ask, the contract assert is some kind of observable point for the compiler. I mean, like as like a volatile or just like, I mean, to avoid the optimization in the compiler level to change the where it's gonna be called during to that epoch, like.
You mean the contract assert?
Yes, I mean the.
Yeah, you see, we have this checkpoint before and we have the checkpoint after.
Yes.
So the contract assert and the Boolean expression in there, this is an epoch on its own.
Okay, so it is like observable point for the compiler, so compiler should should do the like you know the atomic assert or atomic things, etc. Like it needs to be read it there and write
It,
executed there.
it all depends on what you do in this contract, in these assertions, as they call it.
Yeah.
Does it address your question?
Yes, I couldn't formulate the question, but I got it. Yeah.
So we see here, I would say, at least 3 epochs in the function itself.
But I mean, like, let's say I have some codes before the contract assert, but the compiler can change the location of the call for the contract assert, just like placing the something like.
No.
No.
It can't do that. This is why I said the code is split into multiple epochs. The compiler cannot pass it around
Yes.
anymore. And it cannot optimize across the boundaries of an epoch.
Yes.
For example, if you have an undefined behavior later on, it cannot infer this knowledge, even if from the same function, to the prior point in the function itself.
Okay, exactly that is what I'm asking for.
And this is the entire point of it. You want to make sure, if you have, for example, the section up to line 8, whatever happens there will become visible outside.
Okay.
This is guaranteed. Okay, whenever we have these contract violations, the compiler will then detour in a central contract violation handler and do whatever it means to do then. And now we have spent so much time here, let's speak a little bit more about it. You can change this contract violation handler. It's usually supplied by the system itself, by the implementation. But if you are not happy with the thing that the implementation is doing there, you can replace it with your own code. But this is only one contract violation in the entire program. So what I would rather want to see is multiple contract violation handlers in multiple libraries. But this is my personal opinion. Okay, this is, we have the central handler, and we get a couple of pieces of information that we can use, and we have contract evaluation semantics that are also associated with them. These are inferred usually from the invocation of the compiler itself. You've already seen this quick enforce kind of thing. This is what the standard library, the hardened standard library, is using. Stop immediately, check the condition, but do not go into the contract violation handler, just stop. Whereas what we currently have, this is the ignore semantics. We do not check, we do not detour into a handler, and we do not terminate. We all know what this is. But we now, please let me finish. We have 2 more contract evaluation semantics that we can use. The first one is observe. We check. We go into the contract violation handler in case of a failure. And this is meant for existing code. For example, code that is running for 10 years in your company and you never noticed a problem, but you're not sure, then you can enable this observe semantic and probably log it into a file, and then a year later you look at your logs and see, oh, there's possibly a problem. Maybe we do something about it. But if we are developing new code, the enforce semantic is a better one. We want to make sure that we stop in this case and create a better solution for the problems we have in our new code. We have a question here?
Yes, if the feature ships with a single handler, is it possible that you then go in and change that in a later language provision to different handlers for different libraries? As you said, you would preferred?
Yeah, it's just a proposal by me. I have not proposed it yet. I would rather see that, because in some cases you want to have a library that guarantees a particular evaluation semantic like this one here, but don't want to use this semantic and a handler that is not specific to a particular library. I don't know if this will happen. We are not even having C++26 yet, where we have the central single contract violation handler. Maybe.
It's good to put it at the random access.
Okay.
That's all.
You know
Because
things.
Well, otherwise it's very interesting to just set your code at that address, and if and any exploits to be exactly at that address. So
But
it's good
then-
to put it by the standard to say put it at the random address.
But on the other hand, it's implementation provided. Implementation can do things that you probably can't do.
It's good to not be at the fixed address.
I seriously think we should go on that one topics because we see there's a lot.
So, what's the role of our beloved UBSAN and ASAN, the undefined behavior sanitizer and the address sanitizer from this point? Are they completely replaced by this?
No. No. This is not about undefined behavior in any ways.
And undefined behavior and the address sanitizer. Okay, the address sanitizer. Does this replace the address sanitizer?
And no, this is orthogonal to this kind of stuff. Maybe we should proceed with the... So this was about the contracts feature. There is another proposal that has been discussed, but unfortunately we ran out of time, and this is this particular proposal. You probably heard about it. This is the profiles thing. It's not part of C++26, but I will give you at least an idea what it was meant to be, and I hope it will become a thing, because it totally fits in there. We know C++ is coming from C, and it expanded over time. And we have undefined behavior. This is also coming from C, and in C, a couple of years they have counted. They had, at that point in time, this many points in the language and in the library itself. And C++ expanded, and now we call it, hopefully, C++26. But this undefined behavior taints both C and C++. We have our share of undefined behavior, so we are not completely innocent. But with erroneous behavior that we've seen today, and with the hardened standard library, now we have parts in our language that can be used without undefined behavior. And this is what I would call contemporary C++ now. And with the profiles, we can expand the space in our language that we can make sure is no longer exhibiting undefined behavior by annotations in the source code, and this is important, in the source code, and tell, okay, for example, we want to make sure that we don't have type violations in there, for example, by reinterpret casts or this use of unions that I've been showing before. And this particular annotation would instruct the compiler to review such code. This is only for new code, obviously. Old code cannot be annotated like this without changing it. But for new code, this is a good guarantee that we want to use. The same with bounds feature, bound safety. This would instruct the compiler to do exactly the same kind of thing that we have in the hardened standard library. I mentioned before, this is an implicit contract, so we allow the compiler to add additional code to every point in the program where we are indexing pointers and might fail there. And there might be even more of that. I don't want to go into details here. This is not a thing in C++ 26, but hopefully it will be in the next version. And this is the part that I will have to skip because of time requirements. So what does it come down to? All the stuff that I've been presenting today, the erroneous behavior contracts and profiles, all of that has to do with the presence of undefined behavior that we have in C++ today. And I was kind of portraying it as being fine, beneficial, and possibly untractable. And this was the prominent stance that we had in the committee in the past decades, I would say. But the times have changed, the compiler technology has improved, and the expectations towards us as developers have evolved. And this means that the committee, the implementers, and we as the entire community, we must adapt to all these new insights that we got in the past and the new realities. And this will be the agenda that will be on our plate in the upcoming years. And let me summarize. Here, speaking about all of these points here. Why do we have to do that? That we should use compile time testing to make sure that we get rid of all of these undefined behaviors and the problems that we might not have seen before. Hopefully use contracts to increase the safety in our systems. And we will see what the future will bring. And never forget this eternal insight. Don't make your program so complicated that your team members and possibly you do not understand anymore what's going on there and run into problems that might affect security or the functional safety. Here are a couple of resources that you might find interesting. They will be in the slides that you get. Here are a couple of ways to ask me more questions if you like to. And with that, I'm finished. Thank you very much.